A fixed quantity of gas at 21 degrees Celsius exhibits a pressure of 752 torr and occupies a volume of 5.12 liters. Okay, that's our conditions here. Got a temperature, got a pressure, got a volume. Calculate the volume the gas will occupy if the pressure is increased to 1.88 atmospheres while the temperature is held constant. Well, if the temperature is constant and we are changing the pressure, this is a Boyle's law problem. P1 V1 is equal to P2 V2. I've got an initial condition. The only thing I have to do is make sure the units are the same, right? So we're changing the pressure in atmospheres. So convert the initial pressure into atmospheres using the definition of torr, and plug into P1 V1 is equal to P2 V2. So if I divide both sides by 1.88 atmospheres, atmospheres cancels, and I get what the new volume is, right? The pressure increases, the volume decreases. B, calculate the volume a gas will occupy if the temperature is increased to 175 while the pressure is held constant. So if the pressure is held constant and we're changing the temperature, this is an example of Charles' law. So we have the pressure in atmospheres, and we have a initial condition, and we're changing it to a new condition. Temperature has to be in Kelvin. All right, so I plug in my initial volume with my initial temperature, and if I increase the temperature, I have to increase the volume, right? This is the relationship here. Increase the denominator, increase the numerator at the same time. So multiply both sides by 628K, cancel Kelvin, and I'm left with the new volume, an increase in volume. Nitrogen and oxygen gases react to form ammonia as follows. All right, so 1 mole of nitrogen reacting with 3 moles of hydrogen makes 2 moles of ammonia. At a certain temperature, and pressure, 1.82 liters of nitrogen reacts with 3.6 liters of hydrogen. If all the nitrogen and the hydrogen are consumed, what volume of ammonia is produced at this temperature and pressure? Okay. As long as the temperature is constant, the pressure is constant, according to Avogadro's law, I can treat liters like moles. So I can talk about 1.2 liters reacting with 3.6 liters of hydrogen to produce how much ammonia. All right, so I guess they were saying they're going to run out together. So if you have 3.6 liters of hydrogen, how much ammonia is going to form? Well, for every 3 liters of hydrogen disappearing, you're making 2 liters of ammonia. So Avogadro's law. All right, 36. Calculate each of the following quantities for an ideal gas. The volume of gas in liters. So we're calculating the volume of gas in liters if I have 1.5 mole has a pressure of 1.25 atmospheres at a temperature of -6 degrees Celsius. All right, so for A, we're using PV is equal to nRT, and we're solving for V. So divide both sides by P, and then just plug in the values. Now, the trick to doing these problems is make sure the units match up with R. R is liter atmosphere mole K, right? 0.0821 liter atmosphere mole K. So moles is moles. Your temperature has to be in Kelvin, so you add 273 to -6. They gave you the pressure in atmospheres, so plug into this and you can figure out what the volume is at these conditions. B, the absolute temperature, right? So this time we're solving for temperature of a gas in which we have 3.33 times 10 to the minus 3 moles at a volume of 478 milliliters. We'd have to get that in liters. At 750 torr. Well, if we're going to use R, we've got to get torr into atmospheres. So we're rearranging PV is equal to nRT to solve for T, so divide both sides by NT. As I said, we have to have our pressure in atmospheres, and we have to have our volume in liters, and we have to have our temperature in Kelvin. So we add 273 to, we're solving for the temperature in Kelvin. right? So we plug into PV over nRT and solve for T in Kelvin. C, pressure in atmospheres. If I have 0.00245 mole occupies 413 milliliters at 138 degrees Celsius. Again, if we're going to use PV is equal to nRT to solve for the pressure in this situation, T has to be in Kelvin, so we add 273 to 138. And the volume has to be in liters, right? So we divide by milliliters by 1,000, get liters, and now we can plug in. Solve for the pressure in atmospheres. D, a quantity of a gas in moles, all right, so we're going to solve for moles. If I have volume in liters, temperature would have to be in Kelvin. Oh, and they gave us the pressure in kilopascals. So rearrange PV is equal to nRT to solve for moles. So divide both sides by RT. And 101.3 kilopascals for every atmosphere, convert to atmospheres. Add 273 to 54 to get it in Kelvin. It's in liters. And plug in and solve for what the moles are. Got half a mole. '53. Calculate the density of nitrogen dioxide gas at 0.97 atmospheres and 35 degrees Celsius. Okay. So P over RT will be equal to moles per liter, right? That's what N over V is. So if I can solve for moles per liter, right, plug in the pressure, plug in the temperature in Kelvin, plug in R, solve for what the molarity of the gas is, I can use the molar mass of nitrogen dioxide to convert to grams per liter, which will give me the density, right? So multiply the molar mass by the by moles per liter. Moles will cancel, and I'll get my density in grams per liter, which, by the way, grams per liter is a perfectly good unit for the density of gases. Calculate the molar mass of a gas if I have 2.5 grams occupying a certain volume, right? 0.875 liters at a pressure, at a temperature. If I knew what the moles were, I could divide moles into grams and get the molar mass. So solve for moles. Plug in your volume in liters. Plug in your pressure in atmospheres. Plug in your temperature in Kelvin. Solve for moles. And then divide moles in how many grams, right? So 3.13 times 10 to the minus 2 moles per every 2.5 grams of gas, right? That's what they told you. So grams divided by moles gives me the molar mass of this gas, 80.2 grams per mole. The metabolic oxidation of glucose in our bodies produces carbon dioxide, which is expelled from our lungs as gas. Calculate the volume of dry CO2 produced at a body temperature of 37 degrees Celsius, 0.97 atmospheres, when 24.5 grams of glucose is consumed in this reaction. All right, so they've given us grams of glucose. They've given us the balanced equation. So it's just, old-time stoichiometry, right? Except this time we want to stop with moles, right? If we know how many moles of gas, we can plug into PV is equal to nRT and solve for the volume of gas. So the first thing is, if you're given 24.5 grams of glucose, use the molar mass to get to moles of glucose. For every 1 mole of glucose disappearing, you're making 6 moles of CO2. Now that you have moles of CO2, you can plug into PV is equal to nRT and solve for the volume. Make sure your temperature is in Kelvin, make sure your pressure is in atmosphere, and solve what the volume is. B, calculate the volume you would need at 1 atmosphere, 298 Kelvin, to completely oxidize 50 grams of glucose. All right, so same problem, different mass of glucose. Use the molar mass of glucose to get to moles. Use the molar ratio to get to moles of oxygen. Once you've got moles of oxygen, you can plug into PV is equal to nRT and solve for the volume again. Twice the mass, twice the volume. A deep sea diver, uses a gas cylinder with a volume of 10 liters and a content of 51.2 grams of oxygen and 32.6 grams of helium. I think I've talked about this before, right? They use helium because it's less reactive than nitrogen under pressure. Calculate the partial pressure of each gas and the total pressure if the temperature of the gas is 19 degrees Celsius. All right, so they gave us grams of both gases. The first step would be use the molar mass of each gas to convert to moles. Then what I want to know is the pressure that each gas is exerting in the tank. So I take moles of each gas, plug it into PV is equal to nRT, right, with a volume of 10 liters and a temperature of 19 degrees Celsius. This many moles, 1.6 moles of oxygen is going to exert a pressure. 8.15 moles of helium is going to exert a pressure. So I solve for what those pressures are. And then according to Dalton's law, the total pressure is just equal to the sum of the partial pressures. I add up the pressures of the helium and the pressures of the oxygen to get the total pressure. A mixture of gases contains 0.75 moles of nitrogen, 0.3 moles of oxygen, and 0.15 moles of CO2. If the total pressure of the mixture is 2.15 atmospheres, what is the partial pressure of each component? So what I need to do in order to figure out what the partial pressure of each component is figure out what fraction each of these components represents. Mole fraction is defined as moles divided by total moles in the mixture. If I know the mole fraction, I can multiply it by the total pressure. The fraction times the total will give me the partial pressure that each one exerts. So total moles is just equal to the sum of all the moles of gases, right? So add up all the moles of gas in my mixture. This will give me total moles. Take total moles, divide it into the moles of each piece. All right, divide it into moles of nitrogen, divide it into moles of oxygen, divide it into moles of CO2 to get the mole fraction of each gas. The fraction multiplied by the total pressure will give me the partial pressure that each one exerts. Boom. And there it is. So 1.3 atmospheres from the nitrogen, 0.54 atmospheres from the oxygen, and 0.27 atmospheres from the CO2.